Okay, so really to start off, we want to acknowledge Gignostics, who are now the owner of the IP and provider for SEEBASE. They purchased the IP from Frogtech a couple of years ago. And we really want to acknowledge well, all our Frogtech colleagues, including Marie-Aude. But I've listed a few key people there who are involved in directly involved in the examples that Zhiqun and I will show this afternoon. So I'll start off looking at SEEBASE and just give a quick overview of the SEEBASE methodology and look at a couple of examples in and around the same area Marie-Aude and Nadège have been talking about. And then Zhiqun, I'll hand over and she'll look more at the magnetic data modeling, how we used it in the SEEBASE products, but just also more generally in some of the issues around, AUTOMAG and getting a good depth debasement using the magnetic data. So SEEBASE, and this image is from the old 2006 Proterozoic SEEBASE, and SEEBASE is a depth debasement surface, but, and SEEBASE itself, if you're not aware, stands for Structurally Enhanced View of Economic Basement. But it's more than just a basement surface. And you can see from this updated image, so this is the Canning Basin area we're looking at, and you can see all that detail, and there's a lot of structural information and interpretation in there. So there's a whole workflow that sits behind SEEBASE, and it's really focused on understanding the underlying basement and everything that is going to affect the rheology of that basement and how that will then impact the overlying basin. It's an integrated, iterative interpretation, pulling together all the data that we have available, and the final image is hand contoured. It's that hand contouring that lets us incorporate those subtle geological features that allows us to be predictive about what we think that basement depth and geometry is. So when we're looking at this, and the Canning Basin is a good example of that, we're starting out, we're really thinking about what affects the rheology, where are those changes. We know from oak crop, we've got the Pilbara there in the west, the Kimberley Craton in the east, and when we can see the Fitzroy Trough, do I need a pointer? Can you see my mouse moving? No.
Yep, we can see your mouse.
Okay, good. So we've got the Fitzroy Trough, and we compare that to the shallow Broome platform. There's clearly a difference in the rheology of the underlying basement. One of the key questions when we start a project is always, what is basement? And I would encourage anybody using SEEBASE to also look at the reports and think about that. If you're lucky and in a given area, economic, crystalline, and magnetic basement will all be the same surface. But in general, it's not that straightforward, and certainly in Northwest Queensland, it's not. Ideally, in this area, you look at several surfaces, and which GA is now doing, and the work I've done for the NT, likewise, I've looked at a couple of different surfaces. This project, which was completed in 2018, the focus was on economic basement for the hydrocarbons within the ISA group, and that, magnetic basement doesn't sit too far below that. In the Murphy province in the north here, the Myali and Kwala are absent, or and then coming down to the Camarga Dome area, the entire Leichhardt super basin is absent. Although it's very thick in the Leichhardt River fault trough, as you come to the west, it's thin and may be completely absent in a lot of those areas. So our definition of SEEBASE basement in this area is at that Calvert level. We're taking the magnetic basement to come through there. Just a point to remember too, as we go to the Eastern Fold Belt basement, crystalline basement is younger because we've got more intense deformation and metamorphism in all the intrusions. And if you come down to the Arandina here, when you're looking at the Georgina basement, crystalline basement's even younger. So it really is a key point to be aware of when you're looking at SEEBASE. So the input data, very similar, a lot of it to what Marie-Aude's just been talking about. we're looking at the gravity, magnetics, surface geology, and then cross sections and seismic, and bringing in, trolling through the literature, looking for the published interpretations, looking at published maps, looking at the uninterpreted seismic data, the drilling data. And again, here, as it's become clear already from the conversations this afternoon, one of the key inputs is a good drill database. In many cases, we have nothing more than location and TD. We don't know where top basement is, or we can't always be confident that it's even been intersected. And then magnetic modeling. And you can see we did a lot of depth modeling in this area, and a test on AUTOMAG for doing basement, defining basement in the shallow cover areas. And Zhiqun will talk about an example shortly. So now the EGGS database, I'm starting a project now. There's a lot of information, additional information in the EGGS database. So as I highlighted earlier, one of the key features that is incorporated is the geological understanding, the rheology of basement, and the structural evolution. So I don't want to get into detail here, but this is just to, highlight. We think about the stress directions during each of the major events. And for example, here with the ISA SuperBase, and we've got the seismic. This is some of the old seismic data here. And you can see the growth package in the river sequence and the thickening in the term. And we would use that then to be more predictive as we move away from the seismic data. And we would incorporate that into the depth of basement model. And that prediction really is key. So just a couple of quick examples of that from the original 2006 SEEBASE interpretation. You can see here on the right, you can see the large depot center interpreted beneath the Beetaloo and the South Nicholson Basin. There was a very limited amount of seismic data at that time, just a few lines in the Beetaloo and a few lines over here in South Nicholson. And the gravity and magnetic data were quite low resolution. And as Nadej has highlighted, we now know there's quite a thick depot center in there. I wouldn't argue with the interpretation of the seismic, but I think some of those deeper units, there is potential for debate on exactly what they relate to. And just to update from the 2018 interpretation, here you can see, I'll just flick back and forth a couple of times. You can see there's a lot more detail in there, and we've got a lot more information now, but the general extent, oops, sorry, I'm going the wrong way. The general extent hasn't changed. So there was a good understanding from that original interpretation. So I will just highlight, this was done in 2018, just before the South Nicholson data really was available. We had it quickly for a quick check at the end of the project. So Queensland now needs to be updated along with the cam and wheel seismic, but there is a new interpretation for the NT that's just in final review. The fault that Nadej has shown, I will refer to in this next slide. And again, looking at our understanding the basement terrains, and that influenced our interpretation through this area. So I've highlighted, we broke the Murphy province into a north and south terrain based on this paired negative positive gravity anomaly. So you can see what I'm really highlighting here in this Murphy South terrain. And it's clearly higher density. We interpret it as an accreted mafic terrain, and we're talking about a very early accretion, well before 1850, maybe well before that. We interpreted the suture to be south dipping. And that's now confirmed from both the seismic line we were just looking at, and again from the MT data, and the detailed MT data highlights the south dipping structures on the southern margin. Our original boundary was further north. You can see there in white. Now with the seismic, we can move it further south with confidence. So in conclusion, for this initial stage, the power of SEEBASE really is that integrated workflow, and it's very, similar to all the data sets integrated with the Exploring for the Future program, but not the same full range of data sets. And we're really focused on understanding the nature of basement, the changes in rheology, and how that then influences the overlying basin. So in the shallow areas, there's a range of methods that have been highlighted this afternoon from GA, and Zhiqun will look at AUTOMAG and some of the testing around that. But the key in the areas of shallow cover is a good drill database. And I think every talk so far this afternoon has highlighted that. And the more we can, with the new systems, with the state and federal government, that's really helping, but there's a lot of historic drill data. And as Rick's question just alluded to, that we don't have enough detailed information compiled in a public form. So if we want a better understanding of the depth to basement through these areas, we have to have the detailed constraints from the drilling. And I'm a fan of GA's new surfaces, and I think it's very complementary to the SEEBASE interpretation. If you want, there's an update to Oz SEEBASE that Geognostics have put out, and you can see and highlight the areas that have been, the updated areas that are now included, and the full NT will come through shortly. I'll hand over to Zhiqun.
Thank you, Karen. Good afternoon, everybody. I'm very happy to have this opportunity to present some of my work. And I'm a consultant geophysicist and previously working for FogTech and currently work for Geognostics. And I will talking about the contribution for finding basement on the cover from the potential field, especially using magnetic techniques, and also will provide some practical examples. Oh, is that correct?
Yes, yes. So
okay,
this is the screen everybody can see.
Okay. I think it's missing something, or just because, yeah. Okay, that's right. I jumped over. Okay. That's my introduction. Karen already talked lots of SEEBASE. SEEBASE provides a comprehensive depth basement structural model. And so what is the contribution from our geophysicists? And firstly, we collect the all variable data in the project area, and we do data evaluation and to do the basic processing, and also combination and doing the stitching. When we get the best quality data, we have done the enhancement processing. And the next part is we have work out the magnetic depth estimation, and work out all the mag models, and work out the gravity modeling. And when the opportunity, we also combined gravity and the magnetic modeling and helping these SEEBASE project. I will talk more about magnetic depth estimation technique and provide some examples. I will go through, we call the 4 anomaly magnetic modeling approach, and I more will talk about AUTOMAG and using this approach to build some shallow SEEBASE. So here is the 1 hour products, the enhancement processing ternary image, and that is composed of 3 filters of tutor, modulus, edge filter. And the left side is gravity, focal gravity, and the right side is RTP. And through this one, you can easily see, very easy to using the information to do the interpretation. And also the subtle anomaly has been highlighted And this image also comprises very strong magnetic, the strong anomalies. And another advantage for this type of enhancement is no sun angle, and so the source body will be better presented and not will distorted or give the wrong location. So in here, I have given the one example. This one is included in the Northwest Queensland SEEBASE project. And the one we have using gravity and magnetic modeling and constrained by seismic and outcrop, and design these things is for test and upgrade SEEBASE interpretation. This work, I work with Karen. We have produced these results. And the bottom is a magnetic basement, and the top is a gravity modeling. And this red dashed line is SEEBASE, and in here shows in the thick blue lines. So now I'm talking some magnetic modeling and the techniques. And for doing this magnetic depth estimation, we have using, I call this three type of approach: forward modeling, inversion modeling, and the combined forward and the inversion magnetic modeling. For the forward modeling, we compute the results from designed models along the profile or grids. The results are used to check magnetic response from geology and the structures. The results are unique. And the inversion modeling is derive a set of source parameters from the observed survey data. The results are non-unique. And the combined forward and the inversion modeling method, this one we have using largely using for our SEEBASE project. We firstly design initial models and the inversion iteration to refine the parameter, finally get the best fit between the observed and the model data. The results are very easy to display and checked with quality. And the same, this one is a non-uniqueness solution. Here is the one example, like we're using the single profile modeling. And when the profile is, for example, like ship track data, they have largely separate. And so for those profile, if you have not control for anomaly striking and the shape, and then in that case, you can get the solution, the variable solution. In here, the one example from the theoretical model, then we do this inversion, you can see the depth error can be easily up to 40%. Here is we call the full anomaly modeling. This one we have using multiple profiles to matching the anomaly in the whole shape. So this method is like we have picking several lines and design initial model, and then run the inversion, and then we can get the good results. The good thing for this method is give you more reliable solution, and but it will take a much longer time if compared with a single profile inversion. And another good thing is you can easily visual, and then you can check the modeling quality, and then get an idea if something's wrong, then you can easily to redo and correcting. This is the one example in the Northwest Queensland project. And as Karen already shows, we have done plenty of the modeling covered in that area. And this one just a very small block. And we based on magnetic anomaly structures, then we have designed the profile cross those anomaly, and usually we have designed this perpendicular to the strike. And then we have working these, for example, in this area has 9 individual sections, and working these simultaneously, and to do the inversion, and then we can get the good results. In here is a section view, and here is a plan view, and also can have a 3D view. And for that forward anomaly approach, we have been using for our all the SEEBASE project. Now I'm talking about AUTOMAG test work for build the shallow SEEBASE. And AUTOMAG was my research during my PhD study in the Adelaide University. And later this program has a module belong to the income technology, and is the one part of model vision. And now, you know, income is now it's a tensor research. So in here, I just give a quick workflow to go through what's this method we have been from the data and achieve to the basement depth. And so what we have, we need to firstly define a region, and then we need collecting all our magnetic data, including line data and all grid data. And also we need to have DEM data. And then we design the model line. And if we haven't got the flight height, we need using terrain data, just like SRTM or DEM data, then we can produce flight height based on the survey information. Then we have created this database, load into the AUTOMAG, and this run AUTOMAG, we need checking the parameter. Sometimes we need to do several test work. Then when we define the good parameter, then we can run AUTOMAG really easily, and we can get those area results pretty quick. And then we will filter out some solution and cut out some bad solution based on some kind of criteria. And when we refine our data points, we will grid the database, grid the depth to the basement. And here is the one example we have done. Actually, it's in the Mount Isa area. We will get this the initial basement depth. Now I give another example. This covered in the Tanamano, South Australia area. And we have using airborne magnetic survey line data. And we have loading this data, and then split the data into different regions. In here is a red line. It's a polygon we have generated based on 1205 SEEBASE. And that's just cut out some outcropping area and also depth deeper than 2 kilometers. Because for AUTOMAG method, it's better working for the shallow depths. It's not good for the deeper depths. So that's the whole area line data. And that is the results derived from AUTOMAG, and that is the preliminary depth results we have generated. So this depth grid with a grid cell size of 500 meters. In the same region, and we have using the GA TMI grid data. The grid data has more advantage because the line data is too big and sometimes to handle, and the storage and also processing has a lot of work need to do. But for GA, supply the very high resolution TMI data, and in that case, we can design our model line and then extracting all the points from the TMI grid. And this is the one example we have working in the GA TMI grid in that area. So that is a preliminary depth calculator. Use this TMI grid data, and that's just do a comparison with the line data derived basement depth. After we have those AUTOMAG solution, it's good for checking the data quality. And in here, we have collected all the basement depths from GA, from GA database. And then we have worked out what is each point for the wells, then compare with the AUTOMAG results extracting from the grids. And so here is the one comparison. But what we often find, we have AUTOMAG results provided is a deeper results. Actually in here, blue is from the AUTOMAG, the red is from the wells, the depth wells. And so for this drill hole information, mostly shows really shallow. And for this particular region, we have looked at the original location and checking the magnetic anomaly. We realize you can easily find this surface drill hole actually is sit into very smooth magnetic anomaly. So in that case, it's not really, you can think about these basement depths, it's such shallow. So the same area, we have using our full magnetic modeling approach to testing these wells and to see what that results come from full model modeling. And in here, actually, that's the line cross that the well. And so this is related to that line. You can see magnetic anomaly is really strong. And then you can see the broad background and superimposed the subanomaly is much sharper. So for my model, I have one set is about 339 meters, and the bottom is 830. And the rest part of the line, you can see this matching very well, but none of these normally indicate the depth is in the surface. And here is the same area, and we just doing some comparison between the SEEBASE, between the AUTOMAG and this full anomaly modeling. And actually in this one, in that particular drill hole area, this normally it shows the two results are very consistent. So now we have questions about these drill hole depths. And it's possible One possible is the basement rocks at the surface are non-magnetics. Another can be thick zone of the non-magnetic overabundant or variant. And the third possibility is possible the drill hole do not reach to the basement rocks. That indicates, and also for this drill hole information is not provided detailed information. So that is our questions. We back to that Konomono examples, and just I want to show in some area when we do this AUTOMAG, and we will see some area is occurred not reliable solutions. For example, in those areas, actually you can see the magnetic anomaly indicate the source should be deeper, but in the initial AUTOMAG solution indicate those shallow. Okay, I should address the red is indicate shallow and the blue indicate deeper. So for that case, we have checking and find some data has very, some may be composed of the superficial material and some actually is maybe artifacts. And so for this data, we have done low pass 2 kilometer filtering and redo this area. Now you can see this provide a more realistic solution. Okay, back to the end. I'm just summarize the AUTOMAG for the shallow SEEBASE. AUTOMAG is a fast and efficient tool for build basement depth. AUTOMAG results contain uncertainty in the shallow depths from ground to 200 meters. Therefore, it can be supplemented by adding AEM information, especially for the shallow depths less than 200 meters. And also, we should include the SRTM data in the area of basement outcrop. AUTOMAG results highlight the depth of a magnetic source body. Other information is required to access which sources are magnetic basement. And the drillings, seismic, SRTM geology, and the structure information should be included to make the products more geologically accurate and realistic. And a SEEBASE steps to basement model require teamwork from geophysicists and the geologists work together and supplied by GIS. All our work is using GA supplied TMI line and grid data. And the software I have using is Tensor Research, Model Vision, and GSoft Authors Montage. Thank you very much.